Welcome back. In my previous video, I have discussed what is the power series, what is the radius of convergence of power series, and some example of radius of convergence of power series, and what is the interval of convergence of power series and radius of convergence of power series. Actually, at first I will say the geometry. Consider the complex field. See, and consider the power series look like n equal to 0 to infinity Cn z minus an. This is the power series. Since this is the power series, that means obviously there exists capital R belongs to closed zero, closed infinity, such that in the region absolute value of z minus a less than r, in this region this power series is convergent, and in the region absolute value of z minus a strictly greater than r, the power series is divergent. Means there exists a ball which is centered a radius r, which is actually bar, and r is the radius of convergence of this power series. In this region, the power series convergent, and this is actually interval of convergence, and here this power series is divergent. And here this is actually sequence of function fnz equal to cn z minus a to the power n. Since this is polynomial, obviously this sequence of function continuous on the region which is defined as fn from bar capital R to complex field C. This sequence of function is convergent because fz equal to series n equal to 0 to infinity cn z minus a to the power n, where this f is defined from also bar to r, capital R to C. In this region this power series is convergent. Okay. Therefore, I hope my all viewers have understood the geometry of power series, and in this region, since this power series is actually convergent, where r is the radius of convergence, that means actually this sequence of function is convergent in this region, because in this region I will get one power series and which is convergent, and for which values of here z the series is convergent. This is called the interval of convergence, and radius of convergence is supremum distance of the z for which the series converges. This is actually the geometry, and there exists a nice theorem. Theorem is there exists one small r which is less than this capital R, which is actually r is the radius of convergence of this power series, such that this series is uniformly convergent on the set bar, which is obviously contain ba capital R. That means here bar, this is the radius of convergent R. In this region the power series convergent. That means there exists one small r which is, this is now ba small r, which contain ba capital R. In this region the power series is uniformly convergent. Why this is? Because obviously this power series is constructed by polynomial function, And we all of us know polynomial function is always continuous. So obviously this is continuous on the set F who is mapped from BAR to complex number. Sorry, here capital R to complex number. And since this is continuous function, therefore obviously this is continuous in this small region. In this small region, this power series is continuous. Here I have taken small region because we all of us know, in my previous video I have seen R is the supremum of the convergence, and at the point R there exists some power series which is not convergent. So I have taken smaller, which is smaller than capital R. And one power series convergent in BAR means this is always convergent in the interior point, but at the supremum point this is convergent. This is may or may not true. In this region always the power series would be convergent, which is continuous function, and since this region is closed, so in this region this function is uniformly convergent. That means the series is uniformly convergent on the region BAR, which contain BA capital R. Another nice theorem, absolute convergence of power series. The statement of this theorem is the series Cn z minus z0 to the power n be a power series around z0 with radius of convergence r. Then z belongs to the disc z0, r. The series Cn z minus z0 to the power n converges absolutely. That means power series convergence means this series also absolute convergence on this region, and for smaller less than capital R the series also converges uniformly on the disc dz0, r. Furthermore, if absolute value of z minus z0 strictly greater than r, then the series an z minus z0 to the power n is diverges. That means this is the disc z0, r. This is called disc of convergence of formal power series. That means a power series actually converges uniformly and absolutely in any region which lies entirely inside the circle of region. See Cauchy-Hadamard theorem. To evaluate radius of convergence, in my previous video I have seen ratio test. By ratio test I have evaluated the radius of convergence. Today I will see one new theorem, Cauchy-Hadamard theorem. By Cauchy-Hadamard theorem we can evaluate radius of convergence easily. The statement of the theorem is, for a power series an z to the power n, here the center is 0, define a number r where r is lies 0 less than equal to or less than equal to infinity by 1 over r equal to limit n goes to infinity supremum of absolute value of an to the power 1 over n. If mod z less than r, then we can tell the series converges absolutely. If mod z greater than r, then that implies the series diverges. If there exists small r such that if this is greater than 0 and less than capital R, then the series converges uniformly on the region z such that mod z less than r. Okay, this is actually the Cauchy-Hadamard theorem, At first I will see one example. Consider the easy example. The series n equal to 0 to infinity z to the power n square. To evaluate radius of convergence, here I will use the Cauchy-Hadamard theorem. The theorem is 1 over r equal to limit n tends to infinity n to the power 1 over n. Here consider this is whole term is an. Then an to the power 1 over n means z to the power n square to the power 1 over n. This is equal to limit n goes to infinity z over n to the power 2 over n. We all of us know this limit n goes to infinity n to the power 2 over n. This value is always 1. Okay. Therefore, these values would be z, and we all of us know this power series is converges when this absolute value less than 1. Sorry, here absolute value, here absolute, and that implies radius of convergence is 1 and interval of convergence is -1 to 1. In this region, the series converges absolutely. Now I will see, is at the end point the power series convergent? When z equal to 1, then the series reduces 1 over n square. Obviously this series is converges, we all of us know. And when z equal to -1, that means this series equal to -1 to the power n over n square. This is also convergent by Leibniz test. Therefore, this power series converges close interval -1 to 1, and this convergence is not only convergence, this is converges also absolutely. Now I will say radius of convergence of this power series. Here also I will use the Cauchy-Hadamard test. Why I will use here Cauchy-Hadamard test? This is actually very important at first. Notice here the power is n square, and Cauchy-Hadamard test is 1 over r equal to limit n tends to infinity supremum of absolute value of a, and value n to the power 1 over n. Here power is n square. That means if we apply the Cauchy-Hadamard test, then this power would be 1 over n by Cauchy-Hadamard test. Then this limit, we can evaluate this limit easily. So if we apply the Cauchy-Hadamard test, then we can evaluate this power series easily. Consider this part is an. Therefore, 1 over r equal to limit n tends to infinity. Consider this part is only n. Supremum of n plus 2 over n to the power n square. Here to the power 1 over n. Okay. Therefore, this value is limit n tends to infinity supremum of n plus 2 over n to the power n. Okay. And notice limit n tends to infinity, this limit supremum of 1 plus 2 over n to the power n. This limit we all of us know, limit n tends to infinity 1 plus a over n to the power n is e to the power n. So the value of limit is square, and this is actually 1 over r equal to square. Therefore, r equal to 1 over square. That means our radius of convergence is 1 over square. I hope my all viewers have understood this question. Why I have used here Cauchy-Hadamard test. Now I will see some easy 3 question. These 3 question is very conceptual but very interesting. Given the power series an z to the power n has a radius of convergence r, then find the radius of convergence of this power series. Series n equal to 0 to infinity n cube a n z to the power n. Second, series n equal to 0 to infinity a n z to the power 3n. Third, series n equal to 0 to infinity a n cube z to the power n. Here given a n z n, this power series has a radius of convergence r. That means by Cauchy-Hadamard test, we all of us know 1 over r equal to limit n tends to infinity supremum of absolute value of a n to the power r, 1 over a. That means r equal to limit n tends to infinity 1 over supremum of absolute value of a n to the power 1 over a. This is the given r. Here we have to find radius of convergence of the power series n cube a n z n. For this, I will apply Cauchy-Hadamard test. Limit n tends to infinity 1 over supremum. Here a n means n cube a n to the power 1 over n. Now this means limit n tends to infinity 1 over supremum of n to the power 3 over n times supremum of a n to the power 1 over n. And this limiting value is 1. That means this is equal to limit n tends to infinity 1 over supremum of a n to the power 1 over n. And this value is given r. Therefore, if the power series a n z n has a radius of convergence r, then also n cube a n z n has a radius of convergence r. Okay. Now I will see the second question. In the second question has given here the power series n equal to 0 to infinity a n z to the power 3n. For this, the power series a n z to the power 3n. For short trick, consider, since here z to the power 3n, consider z cube equal to w. Then the power series reduces a n w to the power n. And given in the question, the power series a n z to the power n has a radius of convergence r. That means limit n tends to infinity a n plus 1 over a n times z to the power n plus 1 over z n. This implies limit n tends to infinity absolute value of a n plus 1 over a n times absolute value of z. And here given this value, since the radius of convergence of this power series is r, therefore this value would be r times mod z, and this power series convergence when mod z less than 1 over r. Therefore radius of convergence of this power series is actually r. Since here our reduces power series is a to the n w to the power n. Therefore, since this is actually similar to this type of power series, so we can tell by this expression absolute value of w would be less than r, and that means the radius of convergence of this power series also r, but here w means z cube. That means this implies z cube absolute value of z cube less than 1 over r. That imply absolute value of z less than 1 over r to the power 1 over 3. Therefore, radius of convergence of this power series is 1 over r to the power 1 over 3, where r is the radius of convergence of our given power series. Okay? OL. Now we have to find the radius of convergence of this power series, this type of power series. Here, the power series look like series n equal to 0 to infinity a n cube zn. What is the radius of convergence of this type of power series? Here we have to find the radius of convergence of the power series a n cube zn, where given the radius of convergence of the power series a n zn is r. That means r equal to 1 over limit n tends to infinity supremum a n to the power 1 over n. Here also I will use to find radius of convergence Cauchy Hadamard test. Here a n equal to a n cube. Therefore, to evaluate the radius of convergence, this would be 1 over limit n tends to infinity supremum of, here n means a n cube, okay, to the power 1 over n. Therefore, this is equal to 1 over limit n goes to infinity supremum of a n to the power 3 over n, okay, and obviously given r equal to n to the power supremum of n to the power 1 over n, this is equal to r. So we can write this is 1 over limit n goes to infinity supremum of a n to the power 1 over n whole cube, and this value is r. Therefore, this value is r. Therefore, this value is r cube. Therefore, when the given power series look like a n cube zn, where the radius of convergence of the power series a n zn is r, then for this type of power series, the radius of convergence is r cube. I hope my all viewers have understood these three power series. How we have to find radius of convergence of this type of power series when given this power series is radius of convergence r. One example, the radius of convergence of the power series n equal to 1 to infinity n cube over 4 to the power n z to the power 5n. Obviously, this is look like this type of power series. We all of us know the radius of convergence of this type of power series is 1 over r to the power 1/3. Okay. So, at first consider w equal to z to the power 5. Then the power series reduces n cube over 4 to the power n w to the power n. Now we have to find what is the radius of convergence of this type of power series. Here also I will use the Cauchy Hadamard test. Limit n tends to infinity. Here a n means 1 over absolute value of n cube 4 to the power n, here supremum, to the power 1 over n. Then this value would be limit n tends to infinity 1 over supremum of n to the power 3 over n over 4, and this limiting value, limit n tends to infinity n to the power 3 over n, this value is 1. So this is 1 over 4. Therefore, r equal to 1 over 4. This is the radius of convergence of this power series. But our given power series is this, and we all of us know when power series look like this type of power series, since radius of convergence of this power series is 1 over 4. Therefore, for this radius of convergence would be 1 over 4 to the power 1 over 5. Okay, because here z to the power 5n. I hope my all viewers have understood this question easily. Okay, well. Today I will stop here. In my next video I will discuss some example of radius of convergence of power series again, because for competitive exam and for higher study this type of concept actually very important. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.